Now, in the previous two lectures, I discussed the static probe and an example on the static probe. In this lecture, which is an important one, I am still talking about flow rate measurement, section 8-8 in your book, and I'm going to discuss another type of flow measurement devices, and those are called obstruction flowmeters. Obstruction means things that will hinder the flow. flow. Okay, obstruction flowmeters, and I'm going to discuss three types of them: an orifice, venturi, and nozzle meter. So let me look at the figure, this image here. What do we have? This is the pipe, and then we are putting something inside the pipe. This thing is a disc. Actually, what you see here is a disc. I mean, inside the pipe, if this is the pipe, I am inserting something like that. مثل السيدي يعني. So the fluid will try to pass through it. Okay, the fluid will try to pass through it, something like this. So as you can see here, so the fluid is trying to pass through it, something like that, and the same applies there. Same applies at the bottom. So I have two diameters. I have D, which is the diameter of the pipe, so I can call it D1 or big D, and then I have the small d, which is the diameter at the orifice, at the throat. Okay, here. So let me just go through the slide. Consider incompressible steady flow of a fluid in a horizontal pipe of diameter d that is constricted to a flow area of diameter d. So I'm constricting أضيج the flow. Okay, I am making the diameter smaller. So how can we measure the flow rate by doing such a thing? How can I, just by putting a disc, okay, inside the pipe and making the flow harder on the fluid inside this pipe, how can I measure the flow rate by doing such a thing? So the mass balance, here is the answer. So we can do this by measuring or by looking at the mass balance and the energy balance, which is manifested in the Bernoulli equation. So I can apply mass balance and I can apply Bernoulli equation between the location before the constriction, point 1. So I can apply the energy balance, mass balance at point 1, and the location where the constriction occurs, and at point 2, for example here, let us say. So I can apply mass balance and I can apply energy balance between these 2 points, and then I can find hopefully something of interest to me. So by the mass balance I can apply this one, that since I have steady flow, then the volumetric flow rate before and after is the same. But then you will say, okay, why volumetric flow rate? We don't have such a volumetric flow rate balance, we have mass balance. I will say, yeah, because this is incompressible flow, so you can multiply rho 2 here and rho 1 here, and you cancel them because rho 1 is equal to rho 2 is equal to rho. And then I can solve for V1. So you just rearrange this equation, you will find that V1 is equal to this relation, the small d by the big D square divided by V2. You can try to do this yourself. And then I can apply also Bernoulli equation between points 1 and 2, and because I am doing it on the same reference, Z1 is equal to Z2, so once you cancel these two, Z1 and Z2, will get the Bernoulli equation. But now we have to have a question, why you are doing this? I mean, in the pitot static probe, you didn't use the mass balance, you just used the Bernoulli equation. You said that V1 is equal to 0 because this is a stagnation point, and you solve for V2, and it was easy. But here we are not doing this. Why we are not doing this? Because neither V1 nor V2 is equal to 0. They are both not equal to 0. So you cannot just use the Bernoulli equation because you have one equation and two unknowns. Yeah, given that the pressure difference is given, the density is given. So you cannot just solve the problem by having the Bernoulli equation by itself. So you have, because you have V1 unknown, V2 unknown, and you have one equation. So here why we need another equation, and in this case the mass balance equation is used to augment it. يعني I need another equation giving me a relation between V1 and V2, and this is here the mass balance equation. So then all what I need to do is I have this relation between V1 and V2. I will just replace V1 square with this. Okay, so I will substitute it here, and then I will solve for V2, and once you do this, you will find that this is V2 in this case. What is the difference? The difference between this one and the static probe is that thing here, which is I mean the numerator is the same, the denominator is different by actually that thing here. So what is this beta? Beta is just the ratio of the diameters, the small diameter divided by the big diameter, which is this one. This is beta. So beta is d by d. And please don't confuse it with the other beta that we had in the momentum flux. If you remember, the momentum flux correction factor. This is different. This is a ratio of diameters. And this V is V2. This is the velocity at the orifice, the velocity at the throat, the velocity at the small diameter. So do you have any comment on the calculated velocity? I mean, will you ask something about it? Is this the maximum velocity? Is this a local velocity? I mean, what about it? So actually this velocity is obtained, which is this velocity here, is obtained by assuming no losses. Actually, we use the Bernoulli equation, and the Bernoulli equation is based on the assumption that I don't have losses. And thus it is the maximum velocity that can occur at the constriction site. So this equation here will give you Vmax then, or V2 max. This is the maximum velocity at location 2. Why the maximum? Because losses are neglected. How do you know? Because I use Bernoulli equation, which is based on this assumption. So in reality, some pressure losses due to frictional effects are inevitable. يعني لا مناص من ذلك. You have to lose some of your pressure because of this. And thus the velocity will be less. لأن في pressure losses, so I cannot maintain the same the maximum velocity at point 2. So I have to consider the losses here. One might wonder that, so why didn't you consider the losses in the case of the beta static probe? You just applied the Bernoulli equation and we're happy with it. Because we said in the beta static probe, we are not disturbing the flow much. We are not causing a lot of pressure drop. So we would just use it as such. In this case, we are disturbing the flow. We are just putting a disc inside the pipe, and this will cause a huge pressure drop. So are there any other losses that might result from the obstruction? يعني the first type of losses is the friction with the walls that I have to consider. Are there other types of losses? Let us look at this animation. As you can see, this is how the flow inside an orifice is taking place. So what's happening here? So still I have the friction with the walls here. So all of this friction with the walls. I have another thing which is happening here, which is called vena contracta. I talked about this before, if you remember. We said it's a place where the fluid cannot utilize the whole diameter. It cannot utilize the whole diameter I just am utilizing part of it, and this will cause also losses. And also I have those eddies. So now I have three types of losses: friction with the walls, vena contractor, and eddies that are happening here. All of those will add together to have a lot of losses. Where is it? Okay. So again, I have eddies, I have vena contractor, and I have friction with the walls, as you can see. So also the fluid stream will continue to contract past the obstruction, and the vena contractor area, as I told you, is less than the flow area of the obstruction. This is the flow area of the obstruction, and this is the vena contractor area, which is also hindering the flow. So how to account for the losses? شلون أنا أدخل losses في الإيكويشن مالتي اللي هي that I got for V2. So both losses can be accounted for, or all the losses, by the incorporating of both losses can be accounted for by incorporating a correction factor called the discharge coefficient. So I want to add to this equation something called discharge coefficient, which is C sub D, whose value, which is less than 1, is determined experimentally. So I will add to my equation something called discharge coefficient to account for the losses, and it is less than 1. Yeah, the maximum value is equal to 1. ليش? Because if CD is equal to 1 and the ideal case with no losses. So then the flow rate for obstruction flow meters is expressed as, and I have this equation which I can use for volumetric flow rate. طبعا without the A, it is just the velocity. طبعا لاحظوا, this is the equation that I got before, and now I am adding the discharge coefficient. Discharge coefficient, if it is equal to 1, then I will have the maximum velocity, معناته ما عندي losses. But once I added the discharge coefficient, this velocity or this volumetric flow rate will be less because of the losses. So where A0 or A2 is the cross-sectional area of the hole. This is the cross-sectional area of the orifice of D of this, which correspond to D2. And beta is equal to this, is the ratio of the hole diameter to the pipe diameter. The value of CD depends on both beta and Reynolds number. So CD is a function of the diameter ratio and it's a function of the Reynolds number. And there are charts and curves to get the CD. Again, this one with no losses. This is V2 max. Okay, V2 max. If I want V2, then I have to insert here CD. If I want V dot, then I have again to insert here شنو A2 or A sub nu or A sub 0. Now the orifice meter, if you want to get the discharge coefficient of it, then it is given by this equation. I don't have to memorize it, you just need to apply it, and it's a function of beta and Reynolds number, as I have just said, where beta shall lie in this range, and the Reynolds number in this range. Now there is another type of obstruction flow meter which is called a nozzle meter. What's a nozzle meter? It is similar to the previous one, but instead of having them like this, I'm just extending them as such. So the flow is coming smoother through them. So of the numerous types of obstruction meters available, one of the most, let us say, used is the flow nozzle meter. But the question is, how can I use this to measure the flow rate? Actually, I can use the same equation because you can still apply, let us say, the Bernoulli equation, energy balance and the mass balance between points 1 and point 2, and then you will get exactly the same equation, the mass balance and energy balance. A question here, do you think that the CD will be more or less here in this case? let me ask you the question another way. Do you think the losses will be more or less here by doing such a thing? So the CD, I will answer this later. So the CD here again is a function of the Reynolds number, and it's a function of beta, which is the diameter ratios. And you can also have the ratios are given here. I mean the values of the Reynolds number, the range. Another type of the flow meters called the Venturi meter, as it is shown here. And what's happening here, the flow is coming through it and then going smoothly out, and the same thing is happening here. So I have gradual contraction and even slower gradual expansion here. So I'm letting the fluid contract through the hole easily, and then even easier way of going out. This is called a Venturi meter. Okay, a Venturi meter. And again, I am measuring the pressure before and at the constriction. So this is how the flow will look like in a Venturi meter. As you can see here, there are no eddies or wakes, dawamat, and there is no vena contracta. There is no vena contracta, there are no eddies. And let me go back. For the nozzle, what do you notice? Again, there is no vena contracta, okay, but you might get some eddies here. Might get some eddies there, okay. So let me then, so let me ask you this question. Arrange the mentioned flow meters in the order of increasing head losses. So which one do you think will have more? Which one do you think will have less? So I believe the lower one will be Venturi meter. Why? ليش? Because in the Venturi meter, as you can see, I just have one type of losses, which is the friction with the walls. I don't have vena contracta, I don't have eddies. However, notice what's happening here. For the flow nozzle meter, what do we have? We don't have vena contracta, the flow is just utilizing the whole diameter, but still I have friction with the walls and I have eddies. And in the orifice, we said we have three types of them. We have the eddies, vena contracta, and the friction, which means I expect that the Venturi will have the lower losses, بعدين the flow nozzle, and the maximum losses will be in the orifice meter. Okay, let me go through this slide with you. I just want to change the color. So the sudden change in the flow area in the orifice meters causes considerable swirl and thus significant head loss or permanent pressure drop. In nozzle meters, the plate is replaced by a nozzle and thus the flow in the nozzle is streamlined. This is what I have just said. As a result, the vena contracta is practically eliminated and the head loss is small. However, flow nozzle meters are more expensive than orifice meters. So I am paying the price. So I don't have a lot of pressure drop, but I'm paying the price of the device itself. It is more expensive. For flows with high Reynolds number, the value of CD can be taken to be 0.96 for flow nozzles and 0.61 for orifices. طبعا بتقول لي زين شلون هذه اكبر 0.96 اكبر شلون عندي less losses. Yes, in this case if CD is more, this means I have less losses. ليش? Because the ideal case is CD is equal to 1, the maximum. So if CD is more, less losses. If CD is less, I have more losses. Okay, in this case. The discharge coefficients of Venturi meters are very high, ranging between 0.95 and 0.99 for most flows. In the absence of specific data, we can take CD to be 0.98 for a Venturi meter. معناته for orifice, CD is equal 0.61. For flow nozzle, it is equal 0.96, and for the Venturi meter, it is equal to 0.98 because it has the smaller losses. So the Venturi meter is the most accurate and the most expensive device of the three. Its gradual contraction and expansion prevent flow from separation and swirling, and it serves only frictional losses on the inner wall surface. This is what I have just said. Venturi meters cause very low head losses, and thus they should be preferred for applications that cannot allow large pressure drops. So it depends on the application. If I can allow a large pressure drop, I will use the orifice. It is cheaper. If I don't want to allow any pressure drops, then I will go to the Venturi. If I can allow little bit more pressure drop, I can use the nozzle because of the more losses there. That depends on the application. My choice will depend on the application. So what I have done this lecture, I talked about the obstruction flow meters. I talked about the 3 types of them: orifice, Venturi, and nozzle. I told you how to get the equation, which can be used to measure the flow rate. It was derived from Bernoulli balance, from energy balance, from Bernoulli equation, and from the continuity equation, which is the mass balance. And then we introduced to it the discharge coefficient to account for the losses. We said we have 3 types of losses: the friction with the walls, vena contracta, and the wakes or swirls, and they are all present in the orifice meter. However, two types of them are present in the flow nozzle, which are the eddies and the friction with the walls, and only one of them is present in the Venturi meter. So this ends this lecture, and in the next lecture I'm going to solve an example on the obstruction flow meters.